Good morning. Today we are going to start off on a course, Structural Analysis 2, which is the second in the series on courses of structural analysis. During this course, over a period of 45 odd lectures, we are going to be covering the various methods that are used for analyzing structures which are known as statically indeterminate. Well, before I start off on the methods, I'm going to spend at least 2 to 3 lectures on reviewing the basic tenets on which structural analysis are based and the methods that I'm going to be using over and over again during this course. Well, let's start off with what I call as the basic tenets of structural analysis. There are 3. If you look at them, 1, equilibrium. Equilibrium. What is equilibrium? It essentially means that when a structure is subjected to loads, the loads and the internal forces developed in the structure are in equilibrium. In other words, the internal forces equilibrate the external loads. Without equilibrium, what you would have is that the structure would start moving, and obviously a structure, a civil engineering structure, you don't want it moving in space. So therefore, the body has to satisfy equilibrium. The second one, kinematics. What is kinematics? Kinematics is the fact that when a structure is subjected to loads, the structure deforms. In other words, under the loads, the structure deforms and takes up an equilibrium state. This equilibrium state is different from what is known as the undeformed shape of the structure, which is the structure when it was not subjected to any loads. Now, this displaced shape, the structure, the displacements in the structure and the strains that are developed due to the deformation in the structure have to be compatible with each other. This is the basic concept of kinematics. And the third and final tenet is very, very basic, and that is stress-strain compatibility. In other words, when you have loads acting on a structure, the body deforms. Due to the deformation of the body, strains are set up various points in the structure, and because of the strains, stresses are developed, and these stresses are what are essentially the internal forces developed in the body. Now, the stress and strain have to satisfy the compatibility condition or the stress-strain relationship. For example, you know the elastic stress-strain relationship, which is governed by the Young's modulus. The stress is given in terms of Young's modulus into strain. This is the simplest kind of stress-strain compatibility that we can discuss. In this course, I shall be essentially referring to only linear structures. What do linear structures mean? In other words, the relationship between the stress and strain is linear, which, if you really look at it, is something in this form. Sigma, the stress, is proportional to this strain. This proportionality is linear. This is what I am going to be looking at during this course. Okay. So therefore, to just review, A structure has to satisfy equilibrium, it has to satisfy kinematics, and it has to satisfy stress-strain compatibility. Without these three, your analysis will never be correct. You have to satisfy all three. We shall see later on that when we deal with what are known as statically indeterminate structures, I'll spend a little bit of time in the next lecture talking about what do I mean by a statically indeterminate structure. But let's assume that we know what a statically indeterminate structure is. So when you want to analyze a statically indeterminate structure, you have to satisfy equilibrium, kinematics, and the stress-strain compatibility. Now, stress-strain compatibility is fundamental because this is something that is held at the basic tenet, is a basic building block on which we develop the entire edifice of structural analysis. So this stress-strain compatibility can never be violated. However, we shall see later on that when we talk about statically indeterminate structures, some methods satisfy equilibrium exactly and kinematics in a global sense. Other methods satisfy kinematics exactly and satisfy equilibrium in a global sense. Understand that when I say equilibrium and kinematics, they have to be satisfied everywhere in the structure. And when I say that kinematics is exactly satisfied, what I mean is kinematics is satisfied everywhere in the structure. And when I say equilibrium is satisfied only in a global sense, I mean that equilibrium at the local level may not be satisfied. However, overall equilibrium of the structure is satisfied. The other methods, they satisfy equilibrium exactly. In other words, equilibrium is satisfied at the local level. And when I say kinematics at the global level, it means kinematics may be violated at the local level, but at the global level, the displacements and the overall strains in the structure are satisfied. Okay. So much for the basic tenets of structural analysis. Now, I want to discuss a little bit about what do I mean by indeterminacy. How do I analyze a structure? Normal structures are always what we know as statically indeterminate. What do we mean by that? We mean that you cannot, remember that in a statically determinate structure, you could satisfy and obtain all the internal forces from the loads by just dealing with equilibrium equations. Remember that in a planar structure, for example, let's take something, a simple truss. What is a truss? A truss, let's look at this. A truss is essentially a structure which is made up of members where each member is what is known as a two-force member. What's a two-force member? If I isolate the member, this member will only be subjected to axial forces. That is a two-force member. In other words, in a truss, each member is only subjected to axial forces. So therefore, let's look at this particular problem. How many unknowns do I have in the structure? Well, let's look at it. It's a simply supported truss. I am going to have, since this is a hinge restrains the lateral motion of a structure. However, it does not stop the rotation of at the particular point. Since it restrains the lateral motion, the movement in the plane, therefore, it is possible that it can generate two reactions. So, these are my unknown reactions. Let's take that I am subjecting this structure to some loads. So, a hinge has two unknown reactions. This is a roller support. A roller support only restrains this direction motion of the structure. So, therefore, it can only generate a reaction perpendicular to the movement direction. So, these are three unknown reactions. So, we have three unknown reactions. What else don't we know? Well, how many members do we have? 1, 2, 3 members. Now, each member has only the axial force in it. In other words, for each member, we have one unknown internal force in the member. And therefore, since we have 3 members, we have 3 unknown member forces. So, how many unknowns do we have in this structure? We have what are known as 6 unknown forces. We have 6 unknown forces. Now, how many equations of equilibrium do we have? Well, let's look at it. At a particular point, how many points? Remember, a point does not have any dimension. Okay? So, how many equilibrium equations? The point is in a plane. So, how many equilibrium equations can we generate? We can generate one, which is sigma fx is equal to 0. Okay. And the other one is sigma fy equal to 0. So, therefore, at a point we can only generate 2 equilibrium equations, sigma fx equal to 0 and sigma fy equal to 0. So, therefore, each point in the structure we can write 2 equations of equilibrium. Okay. So, we can write 2 equations of equilibrium for every point in the structure. How many points are there in this particular structure? A point, or more commonly joint, are where 2 or more members meet or a member meets a support. So, therefore, how many joints do we have in this structure? 1, 2 and 3. So, we have 3 joints and we can write 2 equilibrium equations for every joint. In other words, how many independent equations of equilibrium do we have? 2 into 3, 6. So, we have 6 equations of equilibrium that we can write for this structure. And how many unknown forces do we have? 6. So, therefore, just by solving the equations of equilibrium, we can find out the reactions in this structure and we can find out the internal forces in each of the 3 members. So, therefore, this structure is known as a statically determinate structure. Statically determinate structure. What is a statically determinate structure? A statically determinate structure is one in which you can find out all the reactions, support reactions and the internal forces in the structure without using anything other than the equations of equilibrium. What happens if we have a situation where the number of unknown forces are greater than the number of equations of equilibrium available? Let's look at a structure. Let's look at a simple structure. Again, I am looking at the truss, the same truss. This structure. What happens here? How many unknown reactions? 1, 2, 3, 4. Then there are 4 unknown reactions, 4 unknown reactions, and of course the same 3 unknown member forces. So therefore we have total 7 unknown forces, and remember exactly the same structure, so we only have 6 equations of equilibrium. What happens now? There is no way that you can find out all the unknown forces with just the equations of equilibrium that you have. So, what do you do? How do you solve this problem? This problem is now what is known as a statically indeterminate structure problem. And this course is where we are going to be looking at all the different methods of being able to solve such a problem. Okay. So now, let's review. We are saying that a statically determinate structure is one in which the number of unknown forces that are in the structure, member forces, support reactions, what have you, the number of unknown forces in the structure are equal to the number of equations of equilibrium independent. Remember, it's always very easy to develop equations of equilibrium, and you will find sometimes, for example, if in a plane you take moments at 2 different points on the plane, are they independent? They will give you 2 different equations. Are they independent? No. Why not? Because moment everywhere on a plane, if you remember, moment is a free vector, and therefore the moment equations, the 2 moment equations that you write, are not independent of each other. So be very careful. When we say equations of equilibrium, we actually mean independent equations of equilibrium. So therefore, if the number of unknown forces are equal to the number of independent equations of equilibrium that you can write for the structure, that structure is known as a statically indeterminate structure. If, however, the number of unknown forces in the structure are more than the number of independent equations of equilibrium that you can develop, then it is a statically indeterminate structure. Now, how do you solve such a problem? We are going to spend the next 40 odd lectures just looking at that. So let us not try to solve that problem today itself. Let's just look at what do I mean by degree of static indeterminacy. You must have come across this. You've done it in school. You've also been introduced to it, the concept, in your strength of materials or solid mechanics course, and you have seen it many a time. Degree of static indeterminacy. We shall see later that for certain methods that we will be looking at, the degree of static indeterminacy in the structure determines the complexity of the problem in using those methods. So, this is a very, very important concept. What do you mean by degree of static indeterminacy? Let us go back to this problem. How many unknown forces? 7. How many equations of equilibrium? 6. What is the static indeterminacy? Well, subtract the equations of equilibrium from the number of unknown forces and you have the degree of indeterminacy, static indeterminacy. So, what is the static indeterminacy of this particular structure? 1. It's what is known as a single statically indeterminate, single degree of static indeterminacy, or single degree of static indeterminacy is 1. Okay. So, it's very simple. For truss type structures, it's very simple to determine the static indeterminacy. How do you determine the static indeterminacy? Well, let me define this problem. For a truss problem, let us look at it. How many unknown forces? R, let R be equal to the number of unknown reactions in the structure, all at the supports, and let M be the number of members, truss members in the structure. Now note, if M is the number of members, each member has one unknown member force. Therefore, when you have M number of members, it implies that you have M unknown member forces. So, therefore, total number of unknown forces is equal to M plus R. So, therefore, in a truss, in a planar truss, I am now discussing only planar trusses. What does planar truss mean? Let us look at it. What does a planar truss mean? Let us go back. If you look at this, a planar truss is one where the truss and the loading on the truss are all in one plane. In this particular case, it is in the plane of the paper. So, that is a planar truss. So, now I am looking at planar trusses. So, when you have a planar truss, you have total number of unknown forces equal to M plus R. What are the total number of equilibrium equations? Well, they have to be equal to 2 into the number of joints that you have in the structure. So, I am defining J as the number of joints that you have in the structure. So, the total number of equilibrium, since you have 2 independent equations of equilibrium at each joint, the total number of independent equilibrium equations is 2J. So, then what is the degree of static indeterminacy? And let me write this down very, very carefully, and this is fundamental. The degree of static indeterminacy of a truss structure is equal to M plus R, which are the number of So, therefore, the degree of static indeterminacy of a truss structure is equal to m plus r. M plus r are the total number of unknown forces in the structure minus the number of independent equilibrium equations which are given by 2j. Very simple. This is the formula for determining the static indeterminacy of a truss structure, a planar truss. M plus r, m is the number of members, r are the total number of reaction forces, m plus r minus 2j, where j are the number of joints in the structure. Very simple. You can determine the degree of indeterminacy, and this is the way that you can determine the static indeterminacy of a planar truss structure. Now, let us see how we determine the static indeterminacy of other structures. What other kind of structure do you have? A truss structure, remember, is a structure where each member is subjected to just one unknown member force, an axial force. You have already been exposed to a beam. What's a beam? A beam is a member which is subjected to both axial deformations as well as flexure. Of course, we know these more commonly as beam columns. Why? Because a beam is one which is primarily subjected to flexure. What's flexure? Bending. Whereas a column is one which is primarily subjected to axial deformations. Primarily, remember, there is a difference between a column and a truss member, because a truss member is only subjected to axial forces, only. It cannot be subjected to any other kind of forces. It only is subjected to axial forces, and it only deforms axially. Whereas a column is primarily subjected to axial deformations. That means that a column can be subjected to bending. However, it primarily is subjected to axial deformation and axial forces. Whereas a beam can be subjected to axial forces and axial deformation, but primarily it is to carry, it carries the loads through bending or flexure. So that let's look at a structure that's made up of beam columns. What kind of structure is made out of beam columns? A planar frame. Let's look at a planar frame. Let me draw a planar frame. The simplest kind of planar frame that we can have. It has one column, one and two columns. One column, two column, and one beam. Okay. So this is a plane frame where, if you look at it, the connection, the joint, let's look at this joint. The joint between the beam and column, if I draw it in reality, it looks like this. This is the column, this is the beam. This joint is a rigid joint. In a truss, what does this joint look like? It looks like this. This is what a joint looks like. This is a pin joint, and that is the reason why in a truss, since this joint cannot transfer any flexural forces, the members become axial members. Whereas in a plane frame, this joint is a rigid, continuous joint. And because of that, you can transfer both forces as well as moments at the joint. So, now where we were discussing the degree of static indeterminacy. How do I determine the degree of static indeterminacy of a planar frame structure? Now, let's go back. Let's look at a simple plane frame member, and I'm going to draw a generalized member. Let me draw a ring. This is a ring. So let me draw the ring. Okay. Now let's say that this is subjected to loads because this ring, it's a structure, it's subjected to loads, it deforms. It deforms, and because of the deformation, it is subjected to internal forces. What are the internal forces? Well, I can find out what the internal forces are by making a cut. Make a cut and see what happens in this zone. If we look at this, if I make a cut, and now I'm going to show it. If I make a cut here, what are the forces that I develop at this point? Well, if I look at this, at the cut, and I'm taking now the cut out here, I'm making the cut out here. How many forces? Well, first and foremost, I can generate an axial force. I can generate a shear force, and I can generate a bending moment. This is the notation that I am going to be using during this course. P, axial force, V, shear force, M, bending moment. In other words, if I look at this, these are my internal forces developed at a cut. And note this, that in this particular problem, when I make this cut and I generate these three, can I find them out? Think about it. I can't. These three are unknowns, which I cannot use any equilibrium equation. Think about it. Take any free body that you wish to. Okay? Take a free body. This entire body is a free body. Okay? And we can make two cuts and separate out another free body. This is a free body. So is this. Think about it. Every time I make a cut, how many forces do I release? 3. So if I make a cut and I take this free body, I have 3 forces here, unknown, 3 forces here, unknown. So how many forces do I have? 6. 6 unknown forces. And for one free body in a plane, how many equations of equilibrium can you generate? 3. What are they? Sigma Fx equal to 0, sigma Fy is equal to 0, and sigma moment about any point equal to 0. These are the 3 equations of equilibrium. So think about it. As soon as I release this and I take a free body, how many unknowns? 6. How many equations? 3. What is the degree of static indeterminacy? Well, number of unknowns minus the number of equations of equilibrium. What does that make it? What is the static indeterminacy of this ring? 3. So therefore, this is fundamental. Please understand that this is how we generate it. That a ring has 3 degrees of static indeterminacy. This I am going to be using to find out the static indeterminacy of a plane frame structure. So now, remember, how do I create a ring? Can I take a structure and make it into a ring? Well, actually I cannot. So I have to think a little bit and do it. Let's come back to the problem that I was discussing a little bit earlier. Look at this. This is the plane frame. How do I find out the static indeterminacy of the plane frame? Can I use m plus r minus 2j? What does that mean? Well, let's look at how many reactions do I have. I have 1, 2, 3. 3 unknown reactions. And how many members? 1, 2, 3. So 3 members. How many unknown equations do I have? M plus r is 3, m is 3. So m plus r is 6. How many joints? 1, 2, 3, 4. 4. So if I use my formula, m plus r minus 2j, j is equal to 4, m plus r is equal to 6. What does that give me? The degree of static indeterminacy is minus 2. Does that make sense? Obviously doesn't. What do you mean by degree of static indeterminacy minus 2? Well, actually, whenever the degree of static indeterminacy is less than 0, it essentially means that the structure is unstable and a mechanism. Is this structure unstable and a mechanism? Think about it. It's not. It's a perfectly valid frame. If I subject it to loads, let's say I subjected it to load here. Is this structure going to move? It's going to collapse? No. It's not. So obviously, the formula that I generated for a truss structure, m plus r minus 2j, is not valid for plane frame structures. Please understand this. Over and over again, I have seen students come and I give them a planar frame structure and they come back and tell me m plus r minus 2j. Well, m plus r minus 2j is not valid for a plane frame structure. It is only valid for a truss structure. Well then, how do I find out the degree of static indeterminacy of a plane frame structure? Well, let's go back to the ring. What is the ring? The ring, if you remember, had 3 degrees of static indeterminacy. Can I take any plane frame structure and make it into a ring? Well, actually, it turns out I can. Let's look at, again, the single story, single bay frame, plane frame. And now, instead of having a hinge and a roller support, I'm going to fix it. I'm going to fix it. This in reality is the most common single bay, single story frame, plane frame. And it's fixed at the foundations. This is the most standard thing. So let's look at this. If you look at this particular structure, Think about it, it's fixed over here, it's fixed over here. So for all practical purposes, I could have a situation where this could have something like this. Right? Because it's fixed here, fixed here, fixed here. So I could have a member like here. Okay? And now look at this. Do you look at this member? What does this resemble? Doesn't it resemble your ring? What is the static indeterminacy of this structure? Since it's a ring, it's 3. 3 is the degree of static indeterminacy. So therefore, a fixed single bay, single story frame has a static indeterminacy of 3. What happens if I put another story on top of it? What happens? Well, think about it. How many rings do you have in this structure? You have one ring here and a second ring here. So each ring has 3 degrees of indeterminacy. So a 2-story single bay frame has how many degrees of indeterminacy? 6. Simple, isn't it? Well, now, do I always have to take a fixed support? Well, no. Think about it. Suppose, what do you mean by reducing the indeterminacy? How do you reduce the indeterminacy? Let's look at it. I have this single bay, single frame, which is fixed, right? So it's fixed. It's fixed. Now, this we just discussed that this particular frame has 3 degrees of static indeterminacy. Okay. Now, let me start releasing some of them. Now, let me see, what does a fixed end have? A fixed end stops this point from moving in this direction. So it has 2 unknown support reactions. Plus, at this point, the joint cannot rotate. In other words, it can generate a moment. So, a fixed support has 3 unknown reactions. Let me now say that what I am going to do is, I am going to release the restraint against rotation. What happens? When I release the restraint against rotation, M has to disappear, because M has to be 0. So as soon as I have taken a fixed end and released its rotational capability, what does it become? It becomes exactly the same as a hinge support. Let me do something more. So let me do the same thing over here. So now what I have is, I have made 2 releases in the 3 degree of indeterminacy. I have made 2 releases. One, I have released the hinge, and 2, I have released the rotation here. Okay. Let me do something more. So I have made 2 releases. I am going to make a 3rd release. I am going to allow it to move in this direction. What does that mean? That means I have taken this restraint and put it equal to 0. In other words, how many restraints am I left with at this point? Single one. Look at this structure. What does it resemble? It resembles this. Hinge support at the left end, roller support at the right end. How many releases did I make in the fixed structure to get to the hinge roller? I made one release here, the rotational release here, one release here, which is the rotational release here, and one release here, which is the horizontal movement here. So how many releases? 3. When you take a 3 degree of static indeterminacy structure and put 3 of the forces equal to 0, because that's what I have done. Here I have taken this moment, put it equal to 0. I have taken this, put it equal to 0. I have taken this moment, put it equal to 0. What have I done? I have removed 3 unknown forces. When you remove 3 unknown forces, what do? You essentially make it into a 0 degree of static indeterminacy. What is a 0 degree of static indeterminacy? A statically determinate structure. Therefore, what do? Well, in planar frames, you essentially start off with the ring. Try to create a ring. Well, let's now look at another structure. You might say, well, you're always taking a plane frame structure and trying to make it into a ring. Give me a multi-span beam and show me how you make it into a ring. Well, let me show. This is a typical multi-span beam. Okay, what's the degree of static indeterminacy? Well, the first thing I'm going to do is I am going to start fixing. I'm going to fix. This is a roller support. I'm going to add 2 restraints to this. So think about it. If I add 2 restraints to a roller support, in other words, I'm going to stop it moving in this direction. I'm going to stop it moving. What happens? It develops an unknown reaction here. Okay? I'm also going to stop the rotation here. I'm going to stop the rotation here. So, what have I added? I have added 2 unknown forces to the structure. Remember that. I have added 2 unknown forces in the structure. Okay? So now here, furthermore, I'm going to stop this also. So I'm going to fix this. I'm going to fix this. So how many? I have added 2 unknown forces. So I've added 4 unknown forces. In other words, I had a structure. How many degrees? Well, let's say it was fixed at this end, roller here, roller here. Okay? So now to make it into a fixed, I've added 2 unknown forces here, and I've added 2 unknown forces here. Okay? So now let's look at this problem. How many rings does it have? Think about it. This is 1 ring. This is a second ring. Independent rings. So, how many degrees of indeterminacy does this fixed structure have? Obviously 2 rings, 6. 6. Think about it. 6. Now, to generate these 2 rings, how many unknown forces did I add? 4. 2 plus 2. 4. So that means, what was the original structure? How many degrees of indeterminacy does it have? Well, I have to take off these 2 unknown forces, because these are fictitious unknown forces that I added to make them into rings. So I have to subtract 4, and how many indeterminacies do I get? 2. Well, let me see if I can get this same in another fashion. Think about it. Suppose I remove this. How many, if I remove this, what have I removed? I have removed one unknown force, that was this. Let me also remove this. So, how many unknown forces have I removed? 2. 2 unknown forces I have removed. 2 unknown forces I have removed. When I remove these 2 unknown forces, what does this become? A cantilever. And we know that a cantilever is a statically indeterminate structure. So, by removing 2 unknown forces, I have made it into a statically indeterminate structure. So, what is the static indeterminacy? Well, 2. Think about it. Either way, you get that this is a 2 degree of statically indeterminate structure. That's it. So, therefore, I today have discussed how to generate degrees of static indeterminacy. How to determine the degree of static indeterminacy in a structure. Of course, I have talked only of planar structures. In this particular course, I am going to be only talking about planar structures, because of course, once you can solve for planar structures, you can solve for space structures also. So, therefore, today I have looked at how to determine static indeterminacy of planar structures, be it trusses. If it is a truss, m plus r minus 2j, where m number of members, r number of reactions, j number of joints. Simple. It is a formula. For a plane frame structure, well, add forces to make them into ring, and then you always remember that the number of rings that you have in a structure, the degrees of indeterminacy per ring is 3. So, you will have, suppose you have 2 rings, 2 into 3, 6. How many unknown forces did you add to make them rings? Subtract that. That will always give you the static indeterminacy. Thank you very much for today. Tomorrow I am going to be taking up on another kind of indeterminacy, that is kinematic indeterminacy. Thank you very much.